Hello there. Today I want to start by telling you a little about my former life, before I went back to school and became a biological scientist. My first career was, surprisingly, that of a conservator restorer. So what does a conservator restorer do? And more importantly, what on earth does that have to do with our course? When I tell people that I am actually trained as a conservator, I always get very different reactions. One of my favorite ones, though, was this Polish lady who was like, I know exactly what you do, and carried on to tell me that I basically make canned food products for a living. And actually, she was not too far from getting it right. Conservators try to prevent things from going bad over time. Really, these pictures are probably more accurate, though, about what conservators do. Conservator restorers are museum professionals whose job it is to preserve historical objects so that they can be seen by many people, both now and in the future. It is not always paintings, though, although most of these pictures that I have chosen here may appear so. Well, one of the things that I found myself doing in my career as a conservator was to work on archaeological sites. As soon as an archaeologist digs out an object at the excavation site, it becomes a responsibility of a conservator. And yes, sometimes you do end up working with human remains. And it was that what attracted me to want to learn more about the human body. And as soon as I realized that since I could not unwrap a mummy to have a peek of what's inside, I needed to learn some things about medical imaging. So that's how I ended up becoming a medical imaging professional. But really, the reason why I'm telling you this story is that I ended up specializing on working with archaeological objects made of organic materials. And that has nothing to do with buying organic tomatoes. So I am going to ask you a question. Since my specialty was organic materials, and I did not have to deal with any objects that were made of inorganic materials, what sort of findings from an excavation site would I have had to deal with? And when could I have said, nope, not my specialty, sorry, cannot help you? Well, what you will end up finding is that many materials that we use as humans are organic. So this includes wood, grass, textile fibers, leather, bone, but also diamonds, for an example. So really, anything that was of a living origin. And most importantly for us, anything that contains carbon atoms. Okay, what would I not to have to work with? How about metals and materials made of rocks? This is all the things that are of a non-living origin, and things that we find out to lack carbon atoms in their molecular structure. So carbon and hydrogen are going to be really important for us when we talk about organic chemistry. In fact, you might often hear people saying that organic molecules have a hydrocarbon backbone. And this is true if you look at the molecular structure of many organic compounds. We do remember that these two often come together and form bonds to reach a state where both of them would have a full electron shell. And even more, Often these join as longer molecules of multiple carbon and multiple hydrogen atoms. And they can form these complex shapes that you see some examples on the right-hand side. Their formulas can be quite pretty, really. Don't some of them look a little bit like snowflakes? And these on the right-hand side are actually quite interesting. Let's have a closer look at them just quickly. What you will notice is that they all have a same number of carbons, 5 of each, and a same number of hydrogen atoms, 12 of each. So they all have the exact same combinations of atoms. Yet they take very different shapes, forming very different structures, which then behave very differently in a chemical sense. These are known as isomers. As I said earlier on, carbon forms often the backbone, or in a chemical sense, the so-called skeleton of most organic molecules. And into this basic structure, we can start adding different combinations of atoms, which we know to always have the same chemical properties, and always to react in a same way, regardless to what kind of carbon skeleton it is attached to. These are what we call functional groups. An example that your textbook mentions is hydrophobic and hydrophilic groups. These hydrophobic being ones that avoid waters, and hydrophilic being ones attracted to water. We will talk more about this important concept later on. I will include a list of some common functional groups with this presentation. This is where we will wrap up this for now. And the next talk will discuss the most important biological molecules that you should be familiar in the field of biology.